Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome to this lecture. We thank Moontai flying all the way from Cornell to come here for this week. So he will talk to us about topic modeling, and will be the paper he will present at upcoming NIPS. So we get a preview of his work. He's an extremely productive researcher and our intern, and we appreciate that he spent one more week with us. Okay, thank you. Bye.
Thanks for the introduction. So today, I will present robust spectral inference for joint stochastic matrix factorization and also for topping modeling. This is a joint work with David Bindel and David Mimno, professors in Cornell University. Before going into the outline, I will briefly talk about what's the difference between several learning models. So in machine learning, in order to learn the model parameter, we have roughly two different methods. One is likelihood-based training. We first choose a proper likelihood estimator. Of course, there are a lot of different estimators like pseudo-likelihood or maximum likelihood, map likelihood. And then we form a likelihood function in terms of the model parameters, and then find the best parameter, usually via optimization. But there are another class of method called method of moments, so which is first relate a population moments to the model parameters, and then estimate population moments via sample. And it usually involves solving multiple different equations. So if I compare these two different approaches to learn parameters, the solving likelihood usually uses optimization, which requires multiple iteration that makes the algorithm usually slow. Whereas method of moments, we are solving equations, closed form equations, and speed is relatively fast. And in terms of the estimation quality, unless the likelihood function we design is strictly convex, it's not always optimal. Whereas the method of moments, it's statistically consistent. What I mean by statistically consistent is if we get more and more sample, it always converges to the right estimator. But whenever there is a mismatch between our models and the real data, likelihood-based method has intrinsic power to manage model mismatch, but it's unclear in the method of moments. So one of the biggest focus of this talk is how to handle model mismatch in a specific problem related to topping model. And the method that I'm interested in this paper is using both matrix algebra and probabilistic inference together in the same framework. Then, so I will briefly explain the latent Dirichlet allocation. So we have two hyperparameters for a multinomial distribution, and for each document and nth position, we first sample the topic from the topic distribution of that document. And based on that topic, we sample the word. And this is how the topping model explains the document generation. If I propose the corresponding view in terms of matrix factorization, it looks like this. So we have a word distribution for each topic and topic distribution for each document, mth document. And because of this is a distribution, this matrix is a column stochastic, which means the sum of every column entries are equal to 1. So let's say we have currently only one document in the right-hand side. And this document, the first document, the first topic is the biggest topic, which affects a lot. Then what we are expected to observe in terms of the word level is the duplication of these words, first word and fourth and fifth word. And if the second document contains the second topics and fourth topics a lot, and then the expected document looks like the sum of these words and these words. But in reality, always the model is not coinciding with the real data. So we are observing these noise in here. Now I'm explaining the event space for joint stochastic matrix factorization. So in comparing to the previous LDA model, now we have a pair of topics and pair of words here. So these pair of topics are sampled from topic-topic distribution. And then based on those pair of topic, we are sampling the words. And words are, of course, related to the word topic distribution in here. So the corresponding matrix factorization view looked like this. So now we have a topic-topic matrix. The sum of all entry will be equal to 1. So this is a joint stochastic matrix. And we have word topic matrix here and transpose here. What we observe is here. This is a word-word co-occurrence matrix for just mth document. So in reality, what we observe is containing some degree of noises like this. So the goal in this paper is to decompose what we observed into this fashion. Okay, so I will explain why we are using second-order method rather than the first-order method. So the benefit, which is proven in Arora et al. 2012, unfortunately, the first-order statistics, which is simple word occurrence in each document, is far from the ideal stuff. But fortunately, the second-order word-word co-occurrence matrix converges well to the ideal word-word co-occurrence. This is proved mathematically. So the goal is to decompose the noisy observation of our co-occurrence matrix into those BA-B transpose. And what is called inference here is to recover the word topping matrix B. And in order to do that, we are going to utilize something called separability assumption. What I mean by that is the typical non-negative matrix factorization. The goal is to minimize the difference between C and BA-B transpose, usually in terms of Frobenius norm. But here, just merely doing that will not give us a great result. And usually it produces unrecognizable topics. It's because there's no identifiability guarantee. In some sense, the separability assumption, which I'm going to explain in the next slide, will guarantee those identifiability to this problem. So again, just minimizing C and BA, the difference between C and BA-B transpose is not the goal of this paper. So what is separability? Separability assumption. Each topic K has a specific anchor word SK, which is exclusive to that topic. What I mean by exclusive is described in here. So when that topic is given, we have a positive probability to observe that anchor word, whereas given different topic, there is no probability to observe that specific word. This implies not every document about topic K must contain that anchor word, but every document which contains that anchor word will tell us at least something about that topic. Then, what I mean by anchor word defined in the previous slide correspond to this red blocks here. So this red block is entirely dedicated to the second topic, and this entirely dedicated to the first topic, because there is no probability of seeing this word, fifth word, given another topic. So we have 3 anchor words in this picture.
So is this assumption valid?
This assumption is valid.
Is this assumption valid or not?
Oh, so in real data, it's of course not always valid. But without this assumption, as I said, the decomposition doesn't have an identifiability. So usually all these unsupervised learning, we would like to identify the mixture, different mixture, topping mixture, for example, in this problem, that those mixture are not sufficiently separated to each other without this assumption.
This will group some different topics into one, right?
Oh, no, this actually separates different topics more distinctively.
No, but if the assumption doesn't hold, then it's possible that you see the same anchor word in several different topics. And those, although they are different topics, but you may group those together as well, right?
Oh, it's different because topic is not we can observe. Topic is a hidden variable. So if we have this assumption, what we would like to do in the inference is to create topic which satisfies this assumption as much as possible as we can. And because these anchor words are exclusive to one topic, it actually tries to learn topic as separated as possible. Topic is not we can observe. Yeah. So if I reorder these and push all these red blocks into the above and reorder, then it means B matrix contains diagonal matrix in here, which is called D in this notation. So basically this decomposition will be rewritten into this block diagonal matrix form. And there's already one interesting correspondence. So if I see this first block after the re-enumeration, then the DAD transpose will correspond to certain matrix of the co-occurrence matrix.
So this looks like an extension of the original topic model with the 2 branches. Or is it at the same topic model with a different inference method?
It's not actually exactly same topic model because we no longer have the prior for the word topic matrix part, but it actually subsumes some degree of those all LDA different models. So you will see.
I see. Okay.
I want to know if I missed something.
Mm-hmm.
So can't there be 2 anchor words in the same column?
2 anchor words in the same column in here?
Yeah.
No, there's no way to get those 2 same anchor words in the same column. Because anchor word assumption means if in certain rows there is only one activated cell.
Right.
Yep. And the number of those rows is also hyperparameter.
But I mean, the condition says that you have to be the only non-white thing in your row. It doesn't say anything about your column. And so I don't see why you can't have 2 red ones. You could have the last row could be identical to the next to last row.
Oh, so again, this is not we can observe.
Pardon?
This is not we can observe B. So what we can observe is only C. Then as a user input, for example, in this picture, user, I'd like to learn topic model with topic 3, number of topic 3. Then we are gonna decompose this matrix assuming there is 3 certain blocks in A.
Okay.
Yep.
So it's just another requirement for an anchor word.
It's not another requirement. That's how the inference goes in terms of the directionality. Now you will see the details.
I don't expect them to help me, but I will see them.
Go ahead.
So putting it another way, does that mean even if you have like two anchor words with a thing as a definition, you can just ignore one. Just so for formulation, just using one anchor word, that's enough.
No, because if you'd like to separate the data set into 10 different mixture, you need 10 anchor words.
Yeah, basically that's what Paul asked for. So because you assume you have a diagonal matrix at the top,
Yep,
which means for each column you only have one as well.
yep.
What Paul mentioned is that it's possible that for some topics you have more than one anchor word.
Oh, that is not allowed in this model.
So this is not allowed.
Yep.
Okay.
So every topic must have only one anchor word. So in 2014, there is an extension, theoretical extension. So every topic has multiple different anchor words. I haven't seen any real implementation of that paper, but there's an extension. Yeah. So if I have an anchor word, this is one of the main inference, how to find. So C bar ij is a row normalized version of word-word co-occurrence matrix. So now it's conditional probability given observing one word. What's the probability of observing another word? And because of this equation, in the end, these relation will be hold, which means so each rows in the row normalized co-occurrence matrix will be convex combination of certain rows corresponding to anchor words. And these, the coefficient, the sum of these coefficient will be equal to 1, and these corresponding to the word topping matrix that we've seen in the previous slide. So assuming we somehow know the anchor word, the rest of the inference is just to figure out these coefficients. So assume we somehow learn those anchor words, and then to solve the previous equation is just to solve non-negative least square with simplex constraint. There will be many different methods. Arora et al. Use exponentiated gradient, and there is also active set method. And this is easily parallelizable for each word. That's one of the biggest benefits. And then the inference becomes very simple Bayes rule. So this will be one entry in that B matrix, ik entry. And once we know these convex coefficient based on these method, all these entries could be rewritten based on Bayes rule. So finding anchor words really matter. So at the beginning, Arora et al. In 2012, they tried to solve a lot of LP. Basically, pick one row in the co-occurrence matrix and see whether it could be reconstructed by all the other rows, which is pretty exhaustive method, and it empirically doesn't work at all. And then people developed or use QR with row pivoting, which is very famous method in matrix algebra. So pick one extreme point in those row normalized co-occurrence matrix as initial anchor, and project every other point rows down to the orthogonal complement of that vector and choose the farthest point, and repeat this process again and again until we find k anchors. Of course, these k anchors will never recover the rest of the rows perfectly, and what we are doing is just approximately find best k rows. And this is a greedy method, so it's not even the best, but something we could do in a manageable fashion. So benefits of this anchor word algorithm is as you could imagine, every inference process is deterministic. So there is no random initialization goes, or there is no funky behavior at all. And so once we construct this noisy co-occurrence matrix based on the real data, and then we no longer play with these documents at all. These are the only statistics that we need for the inference. And then we produce an anchor word, which is exclusively dedicated to each topic, which might bring some interpretability. So what's the problem then? This always happens in machine learning, so the real data never follows the model. So in reality, this co-occurrences with rare words makes sparse rows. So if there's a very rare words, happens 1 or 2 times through the document, the co-occurrence with that word is extremely rare, so which makes sparse row. But in terms of the matrix algebra, those rows look like very strange point or eccentric point of that co-occurrence space. So QR with row pivoting algorithm prefers to select those rows. So anchor words are selected as 2 rare words, and the co-occurrence with those anchor words become noisy statistics. And even worse, the co-occurrences between those anchor words is usually diagonally dominant, which means, so one anchor word corresponds to one topic. If this becomes diagonally dominant, we cannot capture any interaction between topics. This is a serious problem. So as a result, all those previous work, they usually use manually crafted document frequency cutoff, which means, they just set some threshold, like if in order for this word to be an anchor word, it must happen at least in 5 different documents, 10 different documents, sometimes 100 different documents. And they measure the held out likelihood again, while in order to measure the held out likelihood, we need to finish the inference process entirely. And then, it doesn't look like it, and change the threshold and measure held out likelihood again. It's extremely painful process. And even with the document frequency cutoff, and if the number of topics is very small, they learn garbage topics and cannot capture interaction between topics at all because of this problem. And even if K is high, the topic quality is poor. So this is discovered recently because the original 2 papers, they all use the synthetic data set, which follows the model pretty well. But in reality, in the real data, the topic quality is very poor. And comparing to probabilistic inference like Gibbs sampling, the entire inference quality is far inferior. So I will show some sample anchor words with the original algorithm, which is called greedy here. So this is New York Times corpus, which is popular in the scene. And as you could see, none of the anchor words are, understandable. And so we had a toy experiment in previous EMNLP paper. We just compressed down this co-occurrence matrix using either PCA or T-stochastic neighboring embedding. And we realized it gives us much better anchor word and even increasing the held out likelihood. But still, we cannot explain well why these work. That explaining those is one of the purpose of this new paper. So I will show some visual example of those anchor words. So this is a 2D or 3D projection of small Yelp Academy corpus. So these is illustrating the word co-occurrence space and the anchor words corresponding to the vertices of the convex hull, because As you might remember, the goal, after getting anchored, the goal is to learn all those coefficients to express all these words by the convex combination of the anchor words. And interestingly, these anchor words corresponding to certain topic of the anchor of the Yelp. And we can also do 3D projection while it looks messy. There's hummus and enchilada here. So what we've done in the new paper coming for NIPS is we study extensively what's the structure, mathematical structure of co-occurrence matrix C. So while I skipped entirely, this has a lot of probabilistic and statistic structure you could see in the paper. But what I'd like to articulate in this presentation is the geometric structure of the C. So C must be low rank and at the same time doubly non-negative. The doubly non-negative matrix is a category of matrix which is entry-wise non-negative and positive semi-definite. So, and by definition, C must be joint stochastic, which means the sum of all entries is equal to 1. And the low rank document is believed to be generated based on small number of topics. So C need to satisfy these 4 different structure at the same time on top of these probabilistic and statistic structure. So obviously, the C must satisfy a lot of different conditions at the same time. And this is a proof, a very rough proof, why C must be the positive semi-definite. I will skip it. So C needs to be this. And in order to make C satisfy all those conditions, we perform alternating projection. So projecting C down to the low rank positive semi-definite space first, and then projecting down to the cone of normalized matrices, then cone of the non-negative matrices, and repeat this process again and again. So the first projection is easily achievable by the truncated eigenvalue decomposition. So rather than doing the full eigenvalue decomposition, which is clearly painful if the vocabulary size is high, we just use, for example, by using power method, just get the first biggest k eigenvalue and reconstruct C based on that eigenvalue. And the projection, orthogonal projection to the cone of normalized matrix is given by this. Briefly, the intuition is the sum must be equal to 1, and compute the difference between the current sum and the ideal sum, and get the average, entry-wise average, and to basically penalize or reward based on that. And the non-negative matrix cone, it's pretty easy. So the algorithm alternate these 3 projections and again until convergence. However, this alternating projection algorithm no longer guarantees the convergence to the global optimum. It's because whereas the first 2 cones, normalized matrices and non-negative matrices, are convex cone, but the positive semi-definite with low rank is no longer convex, whereas simple positive semi-definite is a convex cone. However, AP instead enjoys local linear convergence. So there's a mathematical proof in my paper, but roughly speaking, only about the intuition. So the set of rank K matrices still forms a not bad shape, which is a smooth manifold. And the intersection with the convex cone and smooth manifold is still smooth manifold in almost every rare sense. And so long as our estimator is not too far from the convergence point, it is guaranteed to be converged. And this is one of the theory by Adrian Lewis, 2009 paper. So the rectified anchor word algorithm that we proposed in the paper consists of five different procedures. First, construct a noisy but unbiased estimator, word-word co-occurrence, and then rectify that by using alternating projection so that C will satisfy all the structure of the ideal C. And then find the anchor words in the rectified co-occurrence, recover the word topic matrix via probabilistic inference with Bayes rule, and recover topic matrix A based on the block matrix diagonal decomposition you see in the earlier slide. So it contains pretty simple procedures, and all of these procedures are deterministic. And that's, of course, clear benefit of this method. So I will show the result. So how the rectified co-occurrence looks like. So this is a two-dimensional visualization of the co-occurrence space. So this is from the original algorithm. By the way, the data set is NIPS data set. And the goal is to find the 5 different anchors of this data set. So each dot corresponds to a word, and this is a word-word co-occurrence space. And if I run the original greedy QR with row pivoting, it chooses 5 different vertices like this. And whereas if I rectify the space like this, and then if I choose 5 different anchors on the rectified space, it corresponds to these 5 points. And if I map these 5 points into the original space, it looks like this. So as you could see, the coverage is much higher, and it can explain the rest of the word as a convex combination better. So this is a typical topic result. So the data set is NIPS, and again, I have 5 different topics. So the original algorithm, Aurora et al., if I run the code based on his algorithm and their algorithm, this is the result topic. So everything looks like neuron, layer, hidden, and basically each topic agrees with the unigram distribution of the corpus. Yeah. And in general, in the world of the topic modeling, if the topic inference does not work well, topic simply mimics the unigram distribution. That's typical behavior. And if I run the Gibbs sampling, it gives pretty good topic. One is about the neuron cell topic, or the control theory, reinforcement learning, or object recognition, or speech recognition, neural network stuff, or Gaussian approximation stuff. And if we run the code in our algorithm, it's pretty similar to the probabilistic LDA, even with this small number of topics. So if you actually increase the number of topics drastically, like 200, then still there is a chance to cover all these vertices eventually at the end. So the topic inference quality becomes better. But if the number of topics is not that large enough, there is a large amount of chances that the original algorithm fails because of selecting too eccentric words, rare words, which is not statistically stable. And this illustrates the topic-topic interaction, which is the second part of the inference. So this is coming from the original Aurora et al. Method. So what they did is, while I haven't described, after finding the word topic matrix, which is B, they multiplies the pseudo-inverse of the B to the left-hand side and the right-hand side of the co-occurrence matrices. Of course, right-hand side, the transpose of the pseudo-inverse matrix. And then it gives this result. Of course, this is wrong, because some entries are even negative, and there's no way for the probability becomes negative. And some entries even beyond 1. And the sum is close to 1. That's because its algebraic property satisfy that. And this is another method that we are using in our paper by multiplying those diagonal submatrix to the left-hand side and the right-hand side. Of course, that is so simple method, and there is no way that the original author didn't try that method. But actually, if we try the original, that multiplying diagonal matrix method to recover the topic-topic interaction without rectification, it will look like this. So it's entirely diagonally dominant because of the reasons that I explained before. Again, anchors is likely to be selected as very rare words. Because of that, the co-occurrence between anchor and anchor are extremely rare. And statistically, it's not a good statistics at all. And it makes this diagonal matrices which cannot capture the topic interaction at all. Whereas this is the result from a rectified anchor word algorithm. It captures the topic interaction pretty reasonably if you actually match one topic with the previous topic in here that we learned. These values turn out to be reasonable. And this plot draws the overall quality at just one big image. So we are not only testing our method in the document collection, which are NIPS and New York Times, we can also do this model for the movie and song data. In the movie data, the word correspond to each movie, and document correspond to the collection of movies that each user observed. And in the song data, each song corresponds to a word, and the playlist in each broadcast station plays frequently will be the document. And then we currently have 6 different measures. The recovery indicates how well those rows corresponding to anchor words reconstruct the other rest of the rows. And the approximation error is the Frobenius norm difference between the original co-occurrence matrices and the decomposed factorized matrices. So basically, the approximation error is the traditional metric to measure how successful the matrix decompositions are. And the dominancy is how those topic-topic matrix is diagonally dominant. And specificity is how much each topic is specified from the unigram distribution. And dissimilarity is how well each topic is separated to each other. And coherence is how well each topic coincides with the document. So while this graph may look a little bit messy, the thing that we have to focus is AP and Gibbs and the original baseline method. So if you see the original baseline method, for example, in approximation, the approximation is pretty high, but the AP or our alternating projection method or the Gibbs sampling method, the errors are pretty low. And those behavior agrees across different data set. And also in the recovery error, as you already see in the word-word co-occurrence figure, after the alternating projection, the recovery rate becomes far better. And if you see another measure, the AP and Gibbs follows pretty similar trajectory. It's comparable to each other, which means we finally achieve the comparable result to the probabilistic inference. If you see the original baseline method, they are all far from those probabilistic inference or AP method.
So what is right criterion to judge which
topic is better?
Yeah, which one is
Oh, yeah, that's one of the questions which pops up always in topping modeling. So this is unsupervised clustering. So there's no clear way to judge which is better. So people used to introduce all these different metrics like that I suggested, and also do the human validation at the same time. Yeah.
So human rate, how good it is.
Yeah, so basically, you see this. It's not that hard. And some people, some researchers designed the matrix, some another metrics based on this result, how much each word frequently occurs across different topics like that. But yeah, those are usually subsumed in the metrics that I illustrated in the plots.
So in other tasks, I saw that people use perplexity.
Yeah, perplexity. Perplexity is a held out likelihood measuring.
So do you use?
Yeah, we actually did that. While we didn't include in this paper. Yeah, so because the reconstruction, recovery error drastically goes down, the held out likelihood increased a lot. So the conclusion. So we studied the various mathematical natures of the co-occurrence statistics. And this might be exciting because as all of you know, the word embedding stuff, they are all based on the word co-occurrence. While they are not coming from these topping modeling assumptions, but of assuming there are some clusters of words in the in the natural language, there might be exciting mathematical structures which is desirable for certain embedding. Of course, that will be becoming different based on which task we are tackling. And we develop a principled way to rectify those noisy co-occurrence rather than exploring the documency cutoff again and again exhaustively. And based on this method, we can learn the quality topics even if k is very small. You already seen k is equal to 5 example. And another example, which is in our paper, is in the movie data. K is equal to 15. And if you run the original anchor word algorithm, I think Pulp Fiction appears across every 15 topics as a top movie. And the second, I forgot the name of that movie, but those two movies always top words across every different topic. While, yeah, what we've learned has exciting cluster like Lord of the Ring cluster, and Star Wars cluster, and Walt Disney cluster. And if you actually run the Gibbs sampling method, they gave pretty comparable result. And then we correctly learn the topic interaction in a stable and efficient manner. And as I said, we achieved the comparable result. So these talks are based on these two papers, which I published last year, and it's gonna coming soon in this year. And while I haven't prepared the slide, we are doing several exciting extensions in multiple different fashion. So as one of you might already realize, so the topping modeling contains two different inferences. One is word topic inference, which is of course the main inference. So how each topic is represented by the distribution of words. That part is included in this algorithm. But the secondary inference, which is what's the portion of topics for each document, that part is entirely missing in this algorithm. So that is currently an ongoing experiment. And interestingly, all the original authors in Princeton, like Sanjeev Arora, Ronga, and Ankara Moitra and all of the authors in Cornell are collaborating each other all together for those. And another exciting extension will be like anchor topic, author topic inference. So rather than viewing all those things as a hidden variable, let's say each author of the document, sometimes document has a footprint of the authors. For example, all these papers have a collection of author. And another assumption, which adds one more layer in the generative story, is, oh, this author are interested in blah, blah, blah topics. So author has a topic distribution, and based on that, the observed words are decided. Basically, some authors are interested more in the topics. For me, I'm interested more in probabilistic method. And then based on that, the word that I'm using frequently will be decided. For example, like map estimation or Bayesian. Those is another ongoing extension. And in entirely different field, like privacy issue, or so basically the co-occurrence matrix C is large. If the vocabulary size is just 10,000, it's going to be 10,000 by 10,000 matrix. And save that in the memory is painful. Usually the natural language vocabulary is 100,000. So how to store and do the rectification step without explicitly storing those all entries is exciting question. And even more, how to store that efficiently and do the rectification without violating the privacy. And those are all exciting extension and the future work. Yeah. So again, wrapping up the presentation, so this is a method this is a new inference combining the probabilistic method and the spectral method. And so after forming the co-occurrence matrix, which is a second order moment matrix, we find the anchor words on that matrix, and then based on that anchor words, all the inference process is deterministic and transparent. And the exciting part, I think, you can take to your home for the future work. So it is pretty susceptible to the sample. So if the sample is not enough, the estimation result is pretty bad. And also the model mismatch, there's no intrinsic ability to handle the model mismatch. However, if those are solved, the result from the method of the moment, it's easy to compute efficiently. And if we plug that result into the original probabilistic inference, for example, Gibbs sampling needs a burn-in process. No one knows how many iterations we need to run at the beginning to get a good result. But if we actually plug this result as an initial value to the Gibbs sampling, it shows amazing result which even never appeared in 100,000 of iteration, which is very exciting. So usually all these likelihood function in the likelihood-based method, they are never convex, and there are a lot of modality inside of there. And of course, we cannot find the good initialization point because the parameter space is high dimensional. And this is a really good way to give good initialization. So combining those two methods seems highly promising. And other people's work, there are several other variations. Rather than doing the second moment matrix, some people use third order tensor, which is word co-occurrence. And those tensor decomposition stuff is also another way to do the topic inference, while they need to assume each topic is independent to each other. But yeah, that's another direction in which is done by Anand Kumar group. Yep. So this is the end of the talk.
Thank you very much. Any further questions? So questions are okay.
Pretty short.
Okay.
Yeah, I finished in 30 minutes.
Good. Okay, thank you very much. Yeah.
Thanks.